Okay, so Kim asked me to talk about the two parts of gravity wave sources connected to supermassive black holes and galactic nuclei, one being from the mergers of pairs of supermassive black holes. This is black holes with masses in the million to billions of solar masses range, and then also the gravity wave sources from the capture of stars by those same black holes. So I thought I would try to start by telling you why astronomers believe these things exist. So these are supermassive black holes, SMBH, in galactic nuclei. So the best cases that we know about these black holes are from cases where one measures the velocity of stars as a function of distance from the center of the galaxy. So let's let this be r, the distance from the center of the galaxy. So obviously you have a galaxy, galaxies get brighter in the middle, so the isodensity contours look something like this. And if you're an astronomer, you put a spectrograph slit across there, and you measure from looking at the widths of the spectral lines of the stars from this radius, and this radius, and this radius, and this radius. The widths of the spectral lines tell you the relative velocity, the radial components of the velocities of the stars in each of these pieces, and then you can check the spectrograph slit this way and this way. The galaxies are not spherically symmetric and they do not have isotropic velocity dispersion. So what you really need to do is make a model, but let's pretend that it's all spherically symmetric and isotropic. And typically what you see is that the velocity dispersion, the radial velocity, so in each line of sight, of course, the stars moving in all different directions, like a hot gas in this room, and the velocity dispersion tells you the velocities of those stars are in that sense. And at large radii, you typically see that if you get far out from the center of the galaxy, the velocities get a little bit less. And as you go in the middle, they tend to level off. And then if you have a very good seeing from the ground that it's a nearby galaxy, or you have time on Hubble Space Telescope, you may notice that it starts to go up again in the middle. And the most spectacular case of this is our own Milky Way galaxy, which happens to be very nearby and therefore unusually easy to see small rises at small radii. And out in the outer parts of the galaxy where we live, this velocity dispersion is something like 140 kilometers a second. Our galaxy actually does a little bit the opposite. It actually drops from 140 to about 100 in the inner part. It is leveled from a kiloparsec to a parsec. And then the velocity in the center of our galaxy begins to rise from 100 kilometers per second and all the way up to 1,000 kilometers a second. Okay. And there's nowhere else in the galaxy except within the tenth of a parsec of the center where there are stars moving at 1,000 kilometers a second. If there were stars moving at 1,000 kilometers a second near the sun, they would escape from the galaxy. They'd be on orbits which directly escape. So the center of our galaxy is very special. One can also look at nearby galaxies. If you look at the center of M31, the Andromeda Galaxy, the brightest nearby galaxy to us, you see a similar thing, although we only see it going up by about a factor of 2, not a factor of 10. The Andromeda Galaxy has two little companions, one of which has a strong nucleus and the other one doesn't. The one with no strong nucleus doesn't show any rise in the center, but the one with the nucleus also shows a very large rise in the center. And these rises, although there are only really 3 of them to which you can actually say this, because in most cases the galaxy is far enough away to see a little bit of a rise, but in the center of our galaxy, and in M32 and M31, sigma is proportional to r to the minus 1/2. And if you remember, the mass enclosed in some radius is approximately sigma squared of r divided by g. If I put it 2 in there if you were being picky, isotropic velocity dispersions. Then you see sigma going like r to the minus a half. That means the mass interior to that radius is approximately constant. That's in contrast to most of the volume of galaxies where the sigma is about constant. And so then the mass is increasing proportional to the radius. And most of this mass is in stars, and you can see the stars and everything. It's about the way you look. The density in stars goes like r to the minus 2, and therefore the mass goes proportional to the radius, and the velocity dispersion confirms that. So this suggests that there's something sitting in the middle, and the starlight density does not increase very rapidly in the center of the galaxies. So the so-called mass to light ratio is increasing in the centers. And so there's some dark thing with an approximately radius independent mass sitting in the galaxy, making the stars orbit faster and faster. So let me say a little bit about this light ratio. In bright galaxies, the luminosity density in the stars, rho star, goes proportional approximately to r to the minus 1 in the centers of the galaxies, whereas in younger galaxies, this density tends to go like r to the minus 2. So in this case, the mass in the stars is going proportional to r within r. And in this case, the mass in the stars within r is going proportional to r squared. Whereas in these cusps, the mass in the cusp is being approximately constant, so that's the origin of this statement. The mass to light ratio is increasing rapidly as you go in. So, what are the black hole masses that one measures? Well, I should explain what the limits on this ability are. Astronomers, to discover this, use telescopes, and telescopes have a finite angular resolution. So, the best angular resolution that we routinely have is with the Hubble Space Telescope, whose resolution theta is about 1/10 of an arc second. So we're clearly only going to be able to see this rise if we can see into the radius, let's call it r black dot or r black hole, where, and this radius is defined by the place where the mass in the black hole becomes greater than the order the mass in stars interior to radius r. Right? Outside this radius, most of the mass interior to some radius is in stars. And the stars going like r or r squared. So this is star dominated. The black hole is just some tiny little perturbation sitting in the middle of a great big galaxy. But when I get close enough to the black hole, there are not very many stars that close to the black hole until the black hole begins to dominate the dynamics. And that happens at this radius. So we'll define our black hole by the place where the mass in the black hole is equal to mass in stars interior to that radius. So if we want to see this rise, we need to have, if this is the distance to the galaxy, the angular resolution times the distance must be less than the radius where the black hole begins to dominate the dynamics. Otherwise, when we take our spectrum, we can only measure the velocity dispersion of the stars out here, and we're never going to notice the black hole. Okay, so if we put in some numbers, this is 1/10 of an arc second, so that's 2 by 10 to the minus 6. 1 over 2 by 10 to the 6 radians. That says that the distance is less than 2 megaparsecs times the mass in the black hole over 10 to the 7 solar masses times the velocity dispersion scaled to 200 kilometers a second squared. And just to put in some numbers, if we substitute this expression into here, I've derived that using the result that this R black hole is then the mass of the black hole in units of 10 to the 7 solar masses, sigma over 200 kilometers per second squared parsecs. Plugging this into here.
Plugging what into where?
Sorry?
So just could you point again, plugging what into where? Looking. I just wasn't looking when you pointed.
So this estimate for the mass of the black hole at our black hole is what the disquality happens in the mass of the stars and the mass of the black hole. And this C denotes the central dispersion as opposed to some of the dispersion. Okay, 2 megaparsecs is really, really close. The Virgo cluster is 15 megaparsecs away. The Andromeda Galaxy is 0.7 megaparsecs away. There's only countable number of respectable galaxies within 2 megaparsecs. However, fortunately, there are some black holes which are much more massive than 10 to the 7 solar masses. In the center of our galaxy, it turns out the black hole is 2.5 million solar masses black hole, so we can only see that within a megaparsec. And indeed, the only other galaxy within a megaparsec that has a black hole like that is the one in the companion to Andromeda M32. The Andromeda Galaxy is 210 to the 7, and you can respectively see it even at the megaparsec distance. But there are some black holes of 10 to the 8th and 10 to the 9 solar mass black holes, which you can clearly see at much larger distances, like 20 megaparsecs, in the Virgo cluster. So there's a strong selection effect, but most of what the black holes that we know about in the universe are 10 to the 8th solar masses and above. And the reason is that the volume which we can look at is then, you can see, proportional to the mass of the black hole cube. So there's a big selection effect. When you go off counting black holes, you can see the big ones to much larger distances than the little ones. So if you look at lists of black hole masses that have been measured, and there are about 30 or 40 of them now, depending on how reliably you want to measure them, most of them are dominated by very massive black holes, but that doesn't mean that those are the most common in the universe. It just means that you can see them at much larger distances. Now, if you want to try to figure out what the density of black holes of various masses are in the universe, you then have to correct for this big volume selection effect. So to do that, what people have tried to do is to look for correlations of this black hole mass with things which you can measure in much larger volumes, so that you can try to figure out the volume densities in the universe. And there have been 2 popular correlations, one of which is the oldest and has large scatter. That is the most convenient for extrapolating things, is that the mass in the black hole is about 10 to the minus 3 of the mass in stars in the bulge of the galaxy. Now I say bulge because galaxies generally have 2 pieces. There is the disk, young stars currently forming gas in it, lots of young stars, and there is the bulge, which is typically rather roundish, or at least lemon-shaped or peanut-shaped or something, and consists of much older stars with very little gas and current star formation. And some galaxies are all bulge, and these are called elliptical galaxies. And galaxies which are not elliptical are defined by their so-called bulge-to-disk ratio, and as bulge over disk ratio increases this way, the galaxies are called S0, SA, SD, SD, irregular. And our galaxy is something like SB. People argue about whether it's SBC or SAB or something, but it's something like an SB. The bulge-disk ratio is about 1/4 in our galaxy, so it's not bulge-dominated. On the other hand, most of the big galaxies in the Virgo cluster are ellipticals and S-zeros, which have essentially very little disk at all. And if you ask about the mass density in the universe, most of the mass in stars is actually in elliptical galaxies plus S-zeros. It's not in these galaxies, most of the bulk mass. So another expression which has a small scatter is that the mass in the central black hole is 1.5 by 10 to the 8 solar masses times the velocity dispersion Okay, now you notice there are a lot of significant figures here, and this relationship is somewhat a little bit controversial. This one that I told you here is from Merritt and Ferraresi. If you look, there, despite the 3 significant figures here and the claimed errors, which are in this last significant figure, there's a paper around the same time by Gephardt and Formandy, which gets about 3.6 here. Okay, and there are 2 origins for the big fight. Okay, so plug in. Okay, the origins of the big fights are, first of all, which measurements in this. Of course, there's a large scatter in observational results, and Merritt and Ferraresi claim they've rejected all of the poor measurements and only used the secure ones, and when you do that, you get a steeper slope. And the other subtlety is what you use for this sigma c here. Okay, remember, the velocity dispersion does things like this, and there's also the question of exactly how you define it in the case when you're subtracting a disk from the bulge, for example, in our Milky Way. And although I told you that in the center of our galaxy, this sigma is 110 kilometers a second, in order to get this expression to work so beautifully with small scatter, they use 70. And there's a long 3-page discussion about why they use 70 instead of the measured value of 110. Okay, but doing that makes this have a small scatter.
But the numbers that follow what's good?
Well, no. It's all very solemn and Bayesian and least squares and detailed discussions. But on the other hand, my point is just perhaps don't take it completely seriously. I wouldn't like to go on record as saying anybody fudged anything since this is being recorded. Okay. Okay. So one can now go through, remember I told you a couple of lectures ago about the luminosity density in the universe and the density of stars in the universe. And so one can go and throw out those portions that are in galactic disks and just add up the bulges. And then the density of black holes, supermassive black holes in the universe is just 10 to the minus 3, that in the stars. And so you get this so-called black hole density, 3 by 10 to the 5 solar masses per cubic megaparsec. So that's the sort of, this doesn't tell you, of course, how many there are of any particular mass, it just tells you the integral over all the masses. There's 310 to the 5 solar masses per cubic megaparsec in the supermassive black holes. And you should just compare that to the numbers for stars, which I gave you last few lectures ago. Let me dig that up here. Okay. So that was this M. You'll immediately notice that there's this number is taken out of this Merritt and Ferraresi paper. This is my best one. You'll notice that 10 to the minus 3 of this is a little bit less than this, and this included the disks. Okay, so there's obviously factors of 1.5 slop in there. Okay. The part of the reason is that this number was not derived in this way. So another thing you could do is try to figure out how many galaxies have what sigma c, calculate the volume density of those and do this, and that's sort of what they've done here, except there aren't very many galaxies with velocity dispersion measurements compared to the number with luminosity measurements. So this is a harder calculation. Okay. Okay, so this is the total mass density in the black holes. So we can now ask, how is this broken up? And next time I'll give for Kip to hand out a graph of the luminosity function, but I decided not to give it to you because there are a whole lot of confusing lines and points which cover up the actual one, so I'll try to replot it for you when I have time. But most of the black holes contributing to this mass, so you ask sort of what is the typical black hole mass that's contributing most of that 310 to the 5, it's mostly in 10 to the 7 to 10 to the 8 solar mass black holes. Okay, and the mass function in the black holes, phi of m, is a function of m, looks something like this. It's very steep at the high mass end, relatively flat at the low mass end, and slope -1, where you get most of the contribution to this integral. The integral, if you do an integral phi of m d log m, you care about at this point, and that's around 10 to the 7 to 10 to the 8 solar masses. Now, these black holes are reasonably robustly measured. As I mentioned, at 10 to the 6 solar masses, there's the Milky Way at 210 to the 6, there's one other galaxy at 10 to the 6, and there's M32 at 310 to the 6. So there are really only 3 points down here around 10 to the 6, and it will turn out that these masses of 10 to the 6 are really quite important. Most of the gravity wave sources are going to be these guys, at least locally. They're not going to be these ones. But unfortunately, because of that volume goes like mass cubed effect, we only know this many of these. Okay, so the space density is not very well constrained, especially because we happen to live in our galaxy. M32 has a nice black hole in it, but it's an atypical galaxy. We don't know any other galaxy in the universe that looks like it. And there's one sort of more generic one, but statistics of 1 or 2 objects are not too great. But if you do that, and believe that space density, the space density of 10 to the 6 solar mass black holes is around 10 to the -2 per cubic megaparsec. And of course the space density of black holes bigger than 10 to the 6 solar masses is only a little bit bigger than that because they're most of the total number, although not most of the mass. And you'll notice that if you multiply 10 to the 6 by this number, you get 10 to the 4 solar masses per cubic megaparsec. So those black holes are only about 3% of this total. So it really is mostly from the much heavier ones. Okay, so if you use this expression just for comparison in the volume of the universe less than redshift, some given redshift that I gave you in the first lecture that I gave, the number of these black holes at redshifts less than 1 is 2 by 10 to the 9. Redshift less than 2 is 7 by 10 to the 9. And redshift less than 5 is 2.5 by 10 to the 10. Now, of course, this measurement is really very local, right? It's within 2 megaparsecs, so redshift 0.00001, and you expect probably that the black holes might have had different masses at redshift 5, and we'll discuss that later. But this just gives you an idea that depending on the history of how these formed, there's something of order a few billion to 10 to the 10 galaxies around 10 to the 6 solar masses in the universe, and of course many fewer, less massive ones. Okay, now if you remember that the luminosity function of galaxies looked very much like this, it had slope -1 at the finged end and then dropped exponentially at the high end, and there was a characteristic L star. Where that drop happened. L star in the Milky Way is about half of an L star galaxy. So if you ask today, then an L star, well, remember the Milky Way, by this correlation, has a black hole of 10 to the 6 solar masses. So the black holes, the galaxies that we're interested in and having black holes more than about 10 to the 6 solar masses are galaxies that are brighter than about a third of L star. So galaxies like the Milky Way and brighter. One important thing is that, of course, people have traditionally got the idea that there were black holes in the centers of galaxies, not from these measurements, but 40 years before these measurements, from the discovery of quasars and radio sources in the centers of galaxies. So one can ask the question, what fraction of all these black holes that we're now finding dynamically are actually active in the sense of being a Seyfert galaxy, a radio galaxy, or a quasar? And if one looks at redshift 2, which is the peak of the quasar luminosity function, there are many more quasars at redshift 2 than there are today by a factor of like 100. So if we look back to a redshift of 2, equals 2, the space density of bright quasars, so that's the peak space density is around 10 to the minus 6 per cubic megaparsec. So that's, depending on how you do the calculation, is 2 10 to the minus 4 of the 10 to the 6 solar mass black holes, but these are bright enough that they probably need bigger black holes, so it may be something like 1 in 100 or 1 in 1,000 of these 10 to the 7 or 10 to the 8 solar mass black holes. If you look for faint quasars, and I'll translate these MBs into solar luminosities. The space density is about 3 by 10 to the minus 5 per cubic megaparsec. So that's 1%. And if we look at redshifts less than 1, and you do the most sensitive X-ray surveys you can, looking for any amount of X-ray emission, which can happen even at extremely low accretion rates, you find that about 4% of brighter than L star galaxies are detectably luminous in the nucleus. So that's any sort of accretion onto the black hole. So even locally, it's only 4% of the galaxies which have even any detectable amount of accretion at all onto their central nuclei. So the vast majority of galaxies are ones like the Milky Way and the Andromeda Galaxy, but there is really no signs of activity even at the level of like a few solar luminosities, a few times the luminosity of the sun. Okay, so the vast majority of these black holes are not currently accreting, not making any activity. Okay. Okay, so what about the previous history of these black holes and what might happen in to the supermassive black holes? Well, the model, I guess there are two ways of approaching this. So this is mergers of galaxies. So the empirical approach to mergers of galaxies is that if two galaxies merge, as they merge, the tidal forces of each galaxy upon the other rip stars out of the other galaxy and makes long tidal tails, sort of streamers of stars behind the galaxies. And so the two galaxies, you might imagine, colliding with each other, and in the final state, the two galaxies will merge together and make a new fluffier, slightly hotter galaxy containing most of the stars. But in that initial passage and a couple of subsequent passages, there will be long streamers of stars that will be given the escape energy. And so the merged galaxy will for a while have these tails which gradually expand and get fainter and fainter until they're undetectably faint. And about 30 years ago, L.R. Toomry went through the list of bright galaxies and asked what fractions of them had these obvious tails sticking out. And he did computer simulations to ask how long the tails would be visible and look something like that. And he found that about 1% of respectively bright galaxies had tails with lifetimes of order 2 by 10 to the 8 years, 200 million years. This is L.R. Toomry, 1974. He was also the first, he and his brother Yuri were the first ones to do these famous computer simulations. So there were other people who did them about the same time, but they're the best known in the West. The rest were obscure Brits and Russians who did equally nice simulations, but didn't connect it to the observation so nicely. Okay, so if you take 1% of galaxies have things with lifetimes which are 2% the age of the universe, then it's fairly clear that something like half of all galaxies must have had a merger in the Hubble time. If it was 1 10 to the 8th, then that would say every galaxy must have had a merger in the Hubble time. So it says about 1/2 of bright galaxies must have merged since redshift 1. Of course, the merger rate might have been much higher in the past, but he's just measuring it locally. Okay, so that's an observational statement. Now, currently, most cosmologists with fervent religious enthusiasm believe that the history of the universe is described by cold dark matter, with amplitudes and power spectra are well defined by measurements of the microwave background. And you can drop at least the dark matter down on the computer and allow the structure to grow and allow the resulting dark halos to merge. And then you can identify those dark halos which have the right space densities with galaxies. And you call those things galaxies, and then you find out how often these dark halos merge with other dark halos to estimate a galactic merger rate. And what you find if you do those cold dark matter simulations is this is a so-called merger tree. So this shows a galaxy today, and this is its time history, and the size of the circle is proportional to the mass of the halo which is merging. And you'll see that this galaxy today, its previous history, is that at a redshift of about 0.1, it merged with a little thing which was about 1/10 of its mass, but that at a redshift of 0.3, this bigger one was formed by the merging of something that was about 20% of its mass. And if you go back at a redshift of about 0.4, that was formed by a comparable mass merger. And if you go farther back to initially, it was 7 things, all about comparable mass. And so the cold dark matter is a so-called hierarchical galaxy formation. The first things which formed at high redshifts were the very small subunits, things around 10 to the 8th, 10 to the 9 solar masses. And then as time went on, those little things merged and produced gradually larger and larger things. So in this cold dark matter model for the origin of structure in the universe, the typical galaxy today is predicted to have had of order 1 merger since a redshift of 1 with something bigger than about 1/3 of its mass. So that's consistent with what Toomry noticed observationally 30 years ago. But if you extrapolate even farther back, where we don't have direct observations, it also predicts that every galaxy today formed from the merger of about 100 subunits, each 100th of its present mass. So the CDM so the first is that typical galaxy today was formed by 1 merger with mass ratio greater than about 0.3, since redshift 1.5. Second prediction is that the more massive galaxies formed earlier. Well, I should say more concentrated, actually. And the third statement is that the typical galaxy formed, typical galaxy at redshift of order 10 was of order 10 to the 2 subunits. And depending exactly how you do it. More massive galaxies had more subunits. Okay, so this means if we look at fairly low redshifts where we know that essentially 97% of galaxies, I should have said, when you look at nearby galaxies, let's take this fit as given. So given the measurement of the velocity dispersion in the center of the galaxy, you can predict what the black hole mass should be. Now you can do the following experiment. Look at every galaxy within a distance given by this expression and ask, do you see that mass black hole or don't you? And the answer is yes in 97% of the cases. It's not that only 10% of galaxies have black holes that obey that correlation. It's essentially that everything you look at, which is near enough and we expect to have a large enough black hole to be detectable, you see a rise in the velocity in the center of the galaxy. Okay, so essentially every galaxy which ought to have a black hole obeying this relation has one. We also know that the typical galaxy has had a merger since the redshift 1.5. And we know that the total number of galaxies at redshifts less than 1.5 is of order 5 billion. Okay, so that means if you look out to redshift 1.5, there's roughly one merger every 2 years. And every one of those has a black hole in it, at least locally. So it must be quite a common occurrence for two galaxies, each with an essential black hole of 10 to the minus 3 of its mass, to undergo a merger in which the relative kinetic energy is dissipated into increasing the velocities of the stars in the outer parts, the central parts of the galaxies merge, and then the question is what happens to the two black holes in the center. Now, you notice that if you go back to a redshift of 10, there's now an interesting question. It could be that at redshift 10, only 1 out of 10 or 100 of these little subunits had a black hole in the center, and all the other subunits that merged with them didn't have such black holes in the centers. And the black holes we see today are all the result of growth from the initial 1 out of 10 or 100. On the other hand, it gets a little bit scary if you think that that was true, because remember, we're saying 97% of galaxies actually have something in it. So if only 1 out of 10 of the subunits did, you can do the Poisson statistics, and you find that it's not totally convincing, but it's a little bit worrisome if you started with 10 subunits and only 1 out of 10 has a black hole, and then you typically merge 10 subunits. Quite a lot of them should end up without any black hole in the center. Yet we see 97% of them do. So you might argue that perhaps most of these subunits had little black holes in them. And now, remember, the typical galaxy to a redshift of 10 that we can see out to distances containing 10 to the 6 solar mass black holes, many 10 to the 10 final merged galaxies. So that means that out to a redshift of 10, if each one of these was actually 10 or 100 subunits, then we're talking something like 10 to the 12th subunits which are merging in the age of the universe. So if we could see out to a redshift of 10 in some way, we're talking something like one merger per 0.01 year, or 100 mergers per year of these subunits. Okay, so what happens when these two galaxies, or proto-galaxies, merge? So the first thing that happens is that as the two galaxies pass through each other, of course everything, let's ignore any gas in the system. So these two galaxies, we'll imagine, just consisting of stars, which are point masses. And in our Milky Way, the stars cover 1 part in 10 to the 10 of the sky. So two galaxies pass through each other, each containing 10 to the 10 stars. 1 out of 10 to the 10 of those stars might actually collide, but otherwise they just pass through each other. And it's all point masses, so energy must be conserved. So how do the two galaxies manage to merge? Well, they manage to merge by kicking out some of the orbital energy in these streamers that are ejected to large distances with large velocities, and that allows the rest of the stars in the galaxy to form a merged subunit. So the first stage is that at least the central stars merge, and in that process, remember that the density in the galaxy, density of stars in the galaxy, is a rapidly declining function, typically something like r to the minus 2. So when the two galaxies merge, you might ask, do these stars get all mixed up, or do the stars in the center get sort of sprayed to the outside and the stars on the outside get sprayed to the center? And the answer is no. It takes a lot of energy to do that. So the stars that get ejected into large radii are those from the outer parts, which are not very bound, and the ones in the center, which are tightly bound, stay tightly bound. And so the centers of the galaxies merge with the centers of the galaxies, and the outer parts of the galaxies merge with the outer parts, and there's not very much mixing, which is a big energy cost associated with mixing. And the way that the two centers merge with each other is that, let's look at the point where the outer parts of these two galaxies have merged together, but we still have two distinct nuclei. And there are lots of galaxies which you can see in the universe which look like this. There's a merged outer halo, then two sort of regions about a kiloparsec across. It clearly the galaxy still has two nuclei. So these two nuclei are essentially orbiting each other. They're in their mutual potential, but they're also orbiting through the surrounding stars. And so you can sort of mock this up as imagining that you have a field of stars with some velocity dispersion sigma, and you send some test mass, like the nuclei of one of these galaxies, or perhaps a black hole. You send a little test mass through it at some velocity v test. So as this object moves through the cloud with velocity dispersion sigma, it will perturb the orbits of these stars. And those perturbations are elastic two-body gravitational encounters. If we ignore the collective effects for the moment and just consider the interaction of this moving mass with each of these separate stars, they're elastic two-body collisions. And the cross-section for the two-body collisions, and let's denote that cross-section d squared because I've already used sigma for something else, that cross-section will be, well, if we wanted to have this particle, let's assume it's much more massive than these little test stars of mass m star. If we wanted to get close enough to actually deflect one of their orbits by 90 degrees, then it would have to get close enough that gmt plus m star, let's write this, so a 90-degree deflection occurs when m star sigma squared is of order gmt plus m star. Okay. So this is sort of the binding energy at the pericenter. So another way of seeing that is that the angular momentum, I should put this. Okay, okay. So the MT cancels out, and so we get D is of order. Okay, so that's the estimate of the cross section, and that's the total cross section. But we can also ask how much energy has been imparted to this little test star in that collision. And let's assume that VT is much larger than sigma. Then what happens in the typical collision is that this little star, which let's imagine the collision is viewed from the rest frame of this heavy mass, so its velocity doesn't change very much. In the collision, the velocity of this little star is essentially reversed. And so that means that in the rest frame of this heavy mass, the velocity is just reversed, but in the laboratory frame, it's gained in energy, which is of order Vt, or it's gained a velocity, net change in velocity of order Vt. So the change in energy times the cross section is going to be of order G so that's the cross section, and the change in energy is going to be like m star Vt squared. Okay, so this is like G squared mt squared m star over Vt squared, and I'm assuming here Vt is much bigger than sigma. Okay, so the rate at which I lose energy so the rate at which MT loses energy moving through, okay. Okay.